Okay, let's start our journal club now. It is my pleasure to introduce today's journal club speaker, Junseok Jung from QIA. Junseok is in first year of the Integrated Masters and PhD program at the School of Integrated Technology at Yonsei University, a lab member of Yonsei Quantum Computing Lab. His main research interest is many-body systems in quantum error correction. Today, he will be presenting a talk titled Learning from Quantum Data Reference, sharing insights from the paper predicting many properties of a quantum system from very few measurements by Priskill and others, and Quantum Advantage in Learning from Experiments by Huang and others. Please join me in welcoming Junseok to the stage.
Hello, I'm Jisuk Jung from Yonsei University School of Integrated Technology, and I'm working on many body systems in quantum error correction with Professor Jerome Park. And I'm going to talk about learning from quantum data. This presentation is mostly a paper review of series of papers from Ishin Huang, Richard Kung, and John Preskill, as referred before. So, the motivation of the topic lies within the fundamental concept of science itself. How in the figure below, we can see how scientists learn this state or process is to measure the state or process through observables, store the data, and process it. We could repeat this to make some kind of prediction about the state or process. The author asserts that there exists a quantum advantage in this learning algorithm. First, we'll see about the classical shadow method. The classical shadow method predicts some expectation of observables to learn quantum state of progress. In previous literature, predicting techniques such as quantum tomography suffers from the curse of the dimensionality, which requires exponential number of measurements according to the size. The classical shadow proposed a solution of a polylogrammatic number of measurements. The key point is that we only have to predict some linear features like expectation of the observables. The informal version of the theorem is below. So, the idea is that classical shadows are snapshots of quantum state or progress. The strength of the classical shadow is that the number of classical shadow scales number of measurements needed for classical shadows scales logrammatically of the number of predicting linear features. This is a diagram for this abstract where you can see in the Alice side, we prepare n copies and goes through a random unitary, and Bob measured the n copies. The magic lies in the locus side, where they pick a hard random unitary to apply on and reveal to Bob to predict the observables. So, classical shadows are made of a copy of the original state, which contains measurement outcomes and the unitary operations. It gives a description of the original quantum state observed by a random unitary. And in the figure below, you can see the circuit that has a copy and goes to a random unitary and gives a measurement outcome 1. So a binary measurement outcome 0 and 1. So the classical shadow is a row hat from an inverse measurement channel containing a random unitary and the measurement outcomes. So we do n experiments and get n number of classical shadows. The insight is that the distribution of the classical shadow gives this good description of the original quantum state. That's in the bottom left. Here we can see the distribution of the classical shadow sometimes gives a point for the original quantum state. So the expectation of the trace is same as the original or quantum state. The theorem in the bottom right shows that the the number of quantum states, number of measurements needed goes logrammatically with the number of predicting linear features, and the number of uh, sorry, the number of the predicting features and the shadow norm, which depends on the measurement primitives, so measurement observables, which we'll see later. So here are the results. This is the state of art of the previous literature called the neural network quantum state tomography. Here we can see that the number of experiments goes exponentially with the number of qubits, whereas our classical shadow goes constant. So we have a good classical shadow method, but why do we need a quantum enhanced method, and what advantages that the quantum enhanced methods could give? In before I've said that the classical shadow only is written or is goes according to the measuring observables. For global Clifford circuits or local observables, the shadow norm is irrelevant of the number of predicting features. This case is for learning many features from quantum state, but there are exceptions. For local Clifford circuits or global observables, however, the shadow norm may grow exponentially with the locality. Here we can get our provable quantum advantage. Here in the figure in the bottom right shows that it goes with the power of power 4 with the locality. So the advantage to prove the advantage of the classical, we need some meta representations, which you will see after. The exponential gap between classical shadow and the quantum enhanced method is because of the classical processing suffers from the uncertainty principle for highly incompatible operations, that is the global observable or local Clifford gates. In quantum processing, we can imply an entangling measurement to all the observables to measure it just once, whereas our classical process need exponential measurements. Starting with the SketchUp proof, we go through the tree representation. The state of progress starts with some certain initial states R, and each measurement outcomes resulting from the single experiment causes the state of progress to transit to another node nearby. The entire dynamics process of how memory state will change will be represented by a path from the root to the leaf in the tree, resulting in a distribution made of measurement data. In example, for classical shadow, we can see that we have the initial quantum state, but the measurement outcome is empty because it has been measured. So we go for the first example, we get a bitstring outcome bitstring 00 or 01, 10, and 11. The probability of the bitstring is represented by the thickness of the arrows. So we go through one experiment, second experiment, and polynomial time experiment to get a distribution of exponential measurement data. So why do we need a polynomial repeat of experiments? An arbitrary learning problem can be characterized by hypothesis testing. The hypothesis testing changed the learning problem into a discrimination problem of leaf distributions. As we perform more experiments, the test wait a sec. We set our wanted expectation as the null hypothesis, the distribution that we want, and the other as alternative hypothesis. Here you can see the LeCam's two-point methods show that as we perform more experiments, the depth of the tree increases and the total variation distance between the leaf probability distribution increases. So we can discriminate from what we want and what is the leftover. That is the learning progress. So for example, we can see a Pauli observable, which is a subroutine for many quantum applications. As you can see in the highlights, so we use only order of one copies for the quantum enhanced method, but we actually need 2 powers of n copies for the conventional scenario, or which we have learned, classical shadow. This quantum enhanced method had lots of applications, such as quantum PCA. Quantum PCA, which is principal component analysis, is a quantum state that has the largest eigenvalue, namely the eigenstate with the largest eigenvalue. This may be useful for when sensing a quantum state that is corrupted by noise. So with our quantum enhanced method, we only need order of 1 copies. And for classical shadow, we need order of 2 power and divide it by 2 copies. Also, we can learn a quantum process with these kinds of methods. These are the results, and here we can see that for the state-of-art classical method, the number of experiments goes exponentially with the system size, but our quantum enhanced method goes to almost constant for accuracy over 70%. So we have a great classical method and quantum enhanced method, but can we utilize the quantum enhanced methods from now? But the answer is that only for small, shallow cases. We need a large sustainable quantum memory to do this for large processing. The story for large sustainable quantum memory starts with a topological quantum memory from Eric Dennis in 2002. And the celebrated result came from the Google Quantum AI team in 2024. This figure shows that we can sustain a quantum memory for about 15 hours or more. But this has a very large overhead. So this figure in the bottom right is a good result that has a low overhead with only local measurements. This was the end of my presentation. Thank you. And any questions from the audience?
Thank you for your great presentation. I have a question about classical shadows.
Yes.
So inside you said you prepare like order of 1 density matrices and apply random unit matrices and then measure to approximate the original density matrices. So are those unitary gates has to be n cubic gate, like like hard random n qubit gates, or is it sufficient to just use local hard random gates?
For some observables, it's efficient to only use local observables, but for exceptions like Pauli observables, we need global observables or like local circuit.
So for Pauli measurements, you have to entangle all of the n qubit gates at once.
For Pauli observables that we use, like, just a second. Could you repeat your question?
Okay, so hard random gates, you
Yeah.
can use like hard random U4 gates, like that are hard random 2 qubit gates, or you can use hard random n qubit gates. Theoretically, of course, you cannot do it experimentally. So I'm just wondering, what are the differences of using between the two? Like, is it sufficient to just use arbitrary many numbers of hard random 2 qubit gates when performing classical shadows?
I don't know about how we can make a hard random, but the definition of hard random is that the hard random gate, after measuring the hard random gates, it gives the expectation of values of the observable, I think.
So you're asking, what are the definitions of hard random gates?
What the definition that I remember is that after measurement, it gives the expectation value of the observable. So, just a sec. For our situation, that the distribution of the classical shadow gives a good description, that we implanted hard random circuits, I think. And for some global observables, you can implant it, the unitary gates as globally, but for local observables, that's wrong. For local observables, you can use a local hard random unitary, but for global observables, you should use global hard random, I think.
So it depends on the norm of the Hermitian matrices you would like to measure.
Yes, the measurement observables. So the shadow norms goes with the locality. Mm, uh, it could this be a satisfying answer?
Yeah, thank you.
Okay. Any other questions? If there's not, I'll stop it right here. Thank you.
Thank you, presenters, for the great talk, and thank you, everyone, for attending the seminar today. And we'll end our seminar here.